Most planets keep their secrets buried deep inside. With Jupiter, we thought we had those secrets figured out, either a solid core anchoring it or no core at all. But when Juno got close enough to measure what's really happening beneath the clouds, the results didn't match either idea. Instead, they pointed to something far stranger, something no one had predicted, and it changed the way we look at giant planets forever. For most of the space age, Jupiter's interior was a blank canvas that scientists filled with theory more than observation. We could see its storms, its belts, and its moons with telescopes, but what lay beneath those clouds was guesswork. Two main schools of thought dominated, each with its own logic, each with gaps that no one could close. The first school backed the gravitational collapse model. In this picture, Jupiter was born fast and violently out of the gas of the early solar nebula. Imagine a region of the disk where hydrogen and helium were dense enough that gravity pulled them together like water draining into a funnel. The process would have snowballed, pulling in more and more gas until you ended up with a world over 300 times more massive than Earth. A planet like that would never need a solid seed. Its structure would just be layers of gas and liquid hydrogen stacked endlessly toward the center. If this were true, Jupiter was essentially a star that never ignited. A failed sun without a heart. But there were problems. The collapse model implied a simple composition, hydrogen and helium making up almost everything. Yet every time astronomers looked closer, from Earth-based spectrographs to spacecraft flybys, they found traces of heavier elements. Carbon, nitrogen, oxygen, even noble gases in unexpected amounts. Those didn't belong in a planet that was supposed to be nothing but gas. If gravitational collapse really was the whole story, then where did all those heavy elements come from? The other school backed the core accretion model. This idea borrowed from how the smaller planets formed. First, dust and ice clumped into rocks. Those rocks smashed together into planetesimals. Over millions of years, enough mass gathered to form a nucleus perhaps 10 times Earth's size. Once that rocky seed was in place, its gravity would have been strong enough to pull in the surrounding hydrogen and helium. Gas piled on fast, ballooning into the giant planet we see today. This version solved the heavy element problem neatly. The solid core explained where the metals and ices came from. It also made sense in the context of planet formation models, which predicted that giant planets should start with a core. But this explanation, too, left scientists with questions. How big was the core supposed to be? Was it a dense ball of rock and ice buried under hundreds of kilometers of metallic hydrogen? Or something more complicated? Would such a compact core even survive intact for billions of years under pressures so intense they turn hydrogen into a liquid metal? And if Jupiter really had a solid, well-defined core, why did earlier measurements of the planet's magnetic and gravitational fields remain so ambiguous? By the late 20th century, we had more data but no clear answer. Pioneer and Voyager gave us the first close looks, measuring magnetic fields and radiation belts. Galileo, which arrived in the 1990s, sent a probe straight into Jupiter's atmosphere. It confirmed the presence of heavy elements and hinted that the interior was richer in metals than a pure hydrogen-helium ball should be. But Galileo's instruments could only sample the outer layers, leaving the deep structure unresolved. The core remained hidden, and both the collapse and accretion models stayed alive in the literature. This standoff shaped the way scientists thought about not just Jupiter, but giant planets in general. If Jupiter had no core, maybe gas giants could form almost instantly, collapsing directly out of the nebula. If it had a core, maybe the process was slower and more layered, starting with rock and ice before ballooning into a gas giant. The answer mattered for every exoplanet astronomers would discover in the decades to come. By the early 2000s, the field was restless. Theories were polished, models became more detailed, but the basic divide didn't budge. What was missing was precision. To settle the question, scientists needed a way to look beyond the storms and measure the distribution of mass inside Jupiter itself. That meant going after its gravitational field in far more detail than any mission had done before. This is why NASA built Juno. Unlike the missions that came before, Juno wasn't designed just to take pictures or measure the magnetosphere. It was purpose-built to fly close, skim the cloud tops, and track every subtle tug of Jupiter's gravity. By watching how the spacecraft sped up and slowed down, scientists could reconstruct how mass was arranged inside. It was, at last, a way to move beyond educated guesses. When Juno arrived in 2016 and began its close passes, the expectations were simple: confirm which model was right. Either Jupiter had no core or it had a solid one. But the universe rarely rewards simple answers. The first results in 2017 showed something stranger than either theory had prepared us for. Jupiter wasn't built like the neat diagrams we'd sketched. It was hiding something entirely unexpected. When Juno's results came back in, they didn't fit neatly into either of the long-standing theories. Jupiter didn't have a sharply defined, rocky nucleus anchoring it, but it also wasn't a bottomless column of gas. Instead, the spacecraft's measurements painted a picture of a planet with a fuzzy or dilute core. Heavy elements spread out across a vast region, gradually blending into the surrounding hydrogen and helium rather than sitting as a compact ball in the middle. This discovery raised a simple but difficult question. How do you get a structure like that? Planets aren't supposed to be blurry inside. The conventional models all predicted crisp transitions, a clear boundary between a dense center and the lighter envelope. Juno's data demanded a new explanation. The first idea scientists reached for was the giant impact hypothesis. Proposed as early as the 2010s, following initial hints from Juno's gravity data, this scenario drew parallels to the moon-forming impact on Earth. In the chaotic early solar system, collisions between large bodies were common. Perhaps Jupiter, still young and growing, was struck by another protoplanet, maybe 10 or even 20 times Earth's mass. The energy from such a collision could have shattered a once compact core, scattering heavy elements outward and mixing them into the surrounding layers. This vaporization and hydrodynamic mixing would temporarily create a homogenized envelope, diluting the core's density and mimicking the fuzzy structure Juno detected in 2017. On paper, it was a dramatic but elegant solution, but theory has to stand up to testing. Using supercomputers, researchers ran thousands of simulations of impacts between proto-Jupiter and massive intruders of different sizes, angles, and speeds. Time and again, the results came back the same. The impact would indeed stir the core and disrupt the interior, but not permanently. Over time, gravity would cause the heavier materials to sink again, reassembling into a dense central core. Instead of producing a lasting fuzzy structure, the simulations showed Jupiter would eventually return to something more compact. That mismatch left scientists skeptical that a single violent collision could explain what Juno observed. So, attention shifted to Jupiter's formation itself. Maybe the fuzziness didn't come from destruction, but from birth. In this view, as Jupiter accumulated mass, heavy elements didn't just sink and lock into place. Instead, they partially dissolved into the surrounding hydrogen and helium. Rather than a clean core and a clean envelope, the planet developed gradients, regions where the composition slowly shifts from metal-rich at the center to lighter gases further out. This process would leave behind a diffuse interior without sharp boundaries. Another key factor is convection, the process that normally mixes planetary interiors. On Earth, convection keeps the mantle churning, spreading heat and mixing material. If Jupiter's entire interior were convective, any gradients would eventually be erased, leaving a more uniform structure. But Juno's data suggests that large parts of Jupiter are non-convective, meaning they don't mix efficiently. That stability allows the heavy element gradients to survive for billions of years instead of being smoothed out. This makes the fuzzy core less of an anomaly and more of a natural outcome. Jupiter may have started with a solid core that never stayed compact. Over time, heavy elements blurred outward, mixing with lighter gases, and the lack of full convection preserved that blurred state. What Juno revealed, then, isn't a planet broken by catastrophe, but a planet whose insides evolved differently than the neat layered diagrams we once imagined. Juno's discovery left scientists asking whether Jupiter was just an oddball, or if fuzzy cores might actually be a common trait among giant planets. To answer that, the spotlight turned to Saturn. Luckily, we had a spacecraft sitting there at the right time, Cassini. Following Juno's 2017 to 2021 results, researchers analyzed existing Cassini data, 2004 to 2017, to test if Saturn shared Jupiter's fuzzy interior, leveraging the mission's comprehensive dataset without needing a new probe. Cassini didn't dive into Saturn the way Juno did for Jupiter, but it had a powerful tool: its ability to read subtle waves in Saturn's rings. Those waves aren't just pretty patterns, they're like seismographs. Inside Saturn, vibrations ripple through the planet, and those ripples show up in the rings as little distortions. By studying them, scientists could probe what Saturn looks like deep inside, much like how we use earthquakes to map Earth's interior. When researchers combined Cassini's ring data with gravitational measurements, a clear picture started to emerge. Saturn, too, doesn't have a sharp, solid core. Instead, its interior shows the same kind of compositional gradient: heavy elements concentrated toward the middle, but gradually spreading outward without a clean edge. In other words, Saturn also appears to have a fuzzy core. This was a turning point. If both Jupiter and Saturn share this trait, it's no longer likely to be the result of some rare, random collision. It suggests fuzzy cores are a natural outcome of giant planet formation. Rather than being a strange exception, they might be the rule. And this idea doesn't just stop at our solar system. We've discovered thousands of exoplanets, many of them gas giants even larger than Jupiter and Saturn. If fuzziness is a built-in feature of how these planets grow, then the simple layered models we've been relying on for decades might be far too basic. Gas giants may not have neat separate cores and envelopes, but instead messy, blended interiors that evolve in ways we're only beginning to understand. This changes how we think about more than just structure. It affects how we model a planet's cooling over billions of years, how its chemistry is distributed, even how it might look to telescopes when we measure its atmosphere. In short, Jupiter's fuzziness, echoed by Saturn, forces us to rewrite the rules for giant planets everywhere, from our backyard to distant solar systems. If there's one thing Jupiter is famous for beyond its size and storms, it's its magnetic field. It's the strongest of any planet in the solar system, stretching so far into space that its magnetotail extends beyond Saturn's orbit, 9 astronomical units from the Sun, influenced by solar-wind interactions. But Juno's measurements showed that this magnetic field isn't the simple, symmetric kind we expected from a planet that spins as fast as Jupiter does. Instead, it's lopsided, with strange patches of intensity and even multiple south poles. On Earth, our magnetic field is generated by the motion of liquid iron in the outer core. It's a clean dynamo effect, where Coriolis forces and rotation organize flows into helical patterns that produce predominantly dipolar fields. As the conductive liquid moves, it generates electric currents, which in turn create a global magnetic field. You'd expect something similar on Jupiter, except the conductor there isn't molten iron but metallic hydrogen. Hydrogen that's been squeezed so much by pressure that its electrons are free to move, turning it into a liquid metal. That metallic hydrogen, spinning rapidly with the planet, should drive Jupiter's magnetic field in a fairly straightforward way. But Juno's data showed that things aren't straightforward at all. Jupiter's field is stronger in some places, weaker in others, and highly asymmetrical between the northern and southern hemispheres. It also has spots of intense magnetism that don't fit the simple dynamo model. Scientists had hoped that the discovery of Jupiter's fuzzy core might help explain these quirks. Maybe the diffuse mixing of heavy elements created new kinds of flow patterns that would account for the field's strangeness. The reality turned out to be more complicated. Modeling showed that a stable fuzzy core on its own didn't match the magnetic field Juno observed. In fact, it often produced results that looked even less like Jupiter's actual field. That forced scientists to consider other layers and processes. One possibility is helium rain, droplets of helium separating out of hydrogen and sinking deeper, like oil falling through water. This could change the way heat and material move around inside Jupiter, affecting the flows that generate the magnetic field. Another idea is that Jupiter's dynamo doesn't run uniformly across the planet, but instead operates in different regions with varying conductivity and density. That would naturally create the uneven, patchy magnetic field Juno has mapped. Whatever the cause, the fuzzy core only deepens the mystery. Instead of solving the puzzle of Jupiter's magnetic field, it made it harder to explain. We know metallic hydrogen is a key player, and we know Jupiter's rapid rotation adds energy to the system, but the fine details, why the field is so lopsided, why it has unusual magnetic spots, and why it behaves differently in each hemisphere, remain unanswered. One thing we do know is that this powerful field is directly responsible for Jupiter's incredible auroras. Unlike Earth, where auroras come and go with solar activity, Jupiter's are constant, enormous, and hundreds of times more energetic. They're a visible reminder of just how extreme and complicated the planet's interior really is. Jupiter and Saturn gave us the first clues, but the real test of this idea is out among the thousands of exoplanets we've discovered. For a long time, when astronomers modeled these distant worlds, they used the same simple assumptions we once applied to Jupiter: a solid, compact core with a clean boundary, wrapped in layers of gas. It made the math easier, and without direct data, no one questioned it too much. But Juno and Cassini forced us to rethink those assumptions. If the two biggest planets in our own backyard don't follow the simple rulebook, then why would planets around other stars? Take hot Jupiters, for example. These are a class of exoplanets, planets orbiting stars beyond our solar system, that resemble Jupiter in size and gaseous composition, but orbit extraordinarily close to their host stars, resulting in extreme temperatures and rapid orbital periods. They're blasted with radiation, heated from the outside, and their atmospheres are swollen to enormous sizes. For years, astronomers struggled to explain why so many of them appear puffier and hotter than expected. If you only imagine them as neat, layered planets, they don't make sense. But if you factor in fuzzy cores, regions where heavy elements are blended gradually with lighter ones, suddenly the pieces fit better. Those gradients slow down cooling and change how the interior evolves, helping to explain why these planets stay inflated. This doesn't mean every exoplanet has a fuzzy core, but it tells us we need to be careful. We can't assume that what's inside is simple just because it's easier to calculate. In fact, fuzziness might be the default outcome of planet formation. Instead of clean structures, gas giants across the galaxy may be full of gradients, partial mixing, and blurry boundaries. That changes not just how we picture them today, but also how they might change over billions of years. The challenge, of course, is that we can't send a probe to every exoplanet. The best we can do is observe their atmospheres with telescopes like JWST, measure their mass and radius, and build models to fill in the gaps. Those models are only as good as the assumptions we feed into them. And now, thanks to Jupiter and Saturn, we know our old assumptions were too simple. The next generation of models will have to treat fuzziness as part of the equation. Future missions in our own solar system will also play a big role. Although Juno's extended mission concluded in late September 2025, after relaying its final data before plunging into Jupiter's atmosphere, the wealth of information it returned continues to shape new discoveries. Saturn could be the target of new missions in the decades to come. Every bit of information we gather about how these giants behave up close gives us a better chance of understanding the ones we see light years away. Even with Juno's discoveries, much about Jupiter remains unresolved. We don't know if the fuzzy core is stable or dissolving. We don't know how its gradients have survived for billions of years without being erased by convection. And we don't fully understand how this interior structure ties into Jupiter's uneven magnetic field. These are questions that push planetary science to its limits, and the work isn't slowing down. This year, a team led by Robin M. Meier and colleagues published results from new supercomputer simulations. They modeled massive collisions in Jupiter's early history, the kind of impacts once thought to explain the fuzzy core. But in every scenario, the heavy elements that got mixed outward didn't stay that way. Over time, they sank back down, rebuilding a compact core. Their conclusion was clear. A single giant impact is unlikely to explain Juno's fuzzy core data. Instead, Jupiter's strange interior is probably the result of gradual processes during its formation and evolution, not one catastrophic event. Another group of researchers examined how internal waves move through Jupiter's interior. Just like seismologists use earthquakes to probe Earth's core, these waves can reveal hidden structures in giant planets. The study, by Mathis et al., showed that Jupiter's dilute core changes how sound waves, gravity waves, and inertial waves propagate. In other words, the fuzziness itself could become a tool. If we learn to read these waves, we might finally map Jupiter's heart in more detail than Juno alone can provide. Juno set out to answer a simple question about Jupiter's core, but instead it opened up a bigger mystery. The neat models of a solid heart or no core at all don't fit. Instead, we're left with something far stranger. A fuzzy mix of heavy elements stretching deep into the planet. Saturn shows the same signs, and exoplanets may follow the same pattern, meaning fuzziness could be the rule for giant worlds, not the exception. This changes how we think about planet formation, how gas giants evolve, and how they generate their powerful magnetic fields. It reminds us that even the planets we've lived alongside for centuries can still surprise us. With every answer, Jupiter raises more questions, and that's what keeps pushing science forward.